This is at the bottom of page 46. You need to be able to move from one graph to another. You have a handout there. We're basically going to recreate the table on page 47 because I find that when kids redraw it themselves, then it helps them to remember what's going on. So, when you have, I'll just read here quickly, figure 217 summarizes all the possible dt motions with their corresponding vt graphs and acceleration values. We can use the graph segment shown here to create vt graph sketches from dt graphs and vice versa. So let's go through this. So if you are stopped, the dt graph would be flat. Now, this particular graph shows that the origin is here. You are in fact stopped some distance to the right or to the left of the origin. To the right or the left, those are your two options. Are you to the right or are you to the left of the origin? To the right. And we can say that because the displacement graph here is positive, right? So let's say it's like at a... Yeah, true enough. Let's say it's at 15, I'm making that number up. We would show that this person would actually be stopped 15 meters to the right of whatever they've decided they've called the origin.
What is that called? Initial what? The initial position?
Initial position, I guess, right? Yeah. Okay. The corresponding velocity time graph, you take the slope of this is 0, and you graph the slope. The graph is a consistent 0. So the velocity time graph is here at 0. The velocity itself is equal to 0, so you should just write in here v equals 0. What is the acceleration equal to? It's equal to the slope of this graph, also 0. And the example is the sprinter at rest stopped. Now, I always find this...
Draw this right there.
Pardon me?
Draw it.
I'm going to. See?
Is he dying? Don't go.
Now, go ahead, you draw too.
I think I'm just going to say that they use stopped.
Let's see. If I can draw a stick person...
If I draw it.
Now, remember, I would also draw a start line there because this person is actually to the right of that start line. It doesn't show that in the book. Most people don't start right at... Usually wherever they start is considered the origin, right? So it's kind of a bit of a poor example, but I think they didn't want to put it right at 0. So. The next one down is constant... Oh, sorry. The next one down is also stopped. There's two that are stopped, right? This one just is stopped at a negative position. Like, let's say it looks like it's in the negatives minus 10. VT graph also at 0. Why? Because the slope of the DT graph is 0. The velocity has a value of 0, and the acceleration is the value of the slope, which is also equal to 0. Now, they have the example, they have the person facing in the opposite direction. Oh, I hate when I do that. I do.
Oh, you messed it up. Oh. It's good. We'll understand it. We'll understand it. There you go. Oh. There you go. But you gotta copy it down below.
Oh, that's right.
Gotta move it.
That was a mistake,
Oh,
wasn't
you
it?
just messed it up.
Did I?
No, wait. Did you have to be backwards? Copy and paste.
Now, good question. Excellent.
Oh, no.
You copied in the entire document, didn't you?
Yeah. A great question. Do they have to be facing the opposite direction?
Yes.
I say no.
Because you can just start 10 meters back.
You're just starting 10 meters back. Absolutely. In fact, I think that is just plain old wrong.
Start!
You're gonna raccoon bad boys up.
Hey, Scooby is sitting on the grass.
Great question, though. I think, can you even tell the direction that the person is facing when they are when the diagram shows that they're stopped? And I say no. I personally think that this should be like this, and the only difference is that they're back, and the start line is there. I think that's a better picture of what's actually happening. Now, having said that, if both of these people were facing the other way, would that be exactly the same? Yes, they're stopped. It doesn't matter what direction they're facing, right? There's no vector quantity for facing direction. It doesn't exist, right? When you're stopped, you're stopped. Doesn't matter which direction you're facing. So, anyways. Moving on, constant velocity. So in this one here, the displacement time graph is increasing at a constant rate. The slope is a constant value, so whatever the value of the slope is here is this value here. Let's say it's, I don't know, 5. The slope of the dt graph would be 5, meaning that we would graph a constant 5, meaning that the velocity is equal to the value of 5. That would be the slope of this value, or slope of this graph. And the acceleration is the slope of the acceleration, slope of the acceleration is the slope of the velocity time graph, which in this case is equal to 0. What is our sprinter doing? Running at a constant speed. Running at a constant speed.
You really gotta work on that.
What are you talking about? I've been practicing these for about a week. Let me see yours. That's a very skinny sprinter with no feet, and he's got my haircut though. Running at a constant velocity. Now, if this individual is running backwards, then at a constant speed, the displacement time graph increases at a constant rate like so. The slope of this graph might be, say, -5. That's the slope of this graph. Meaning that the velocity is 5. And once again, the acceleration is the slope of the VT graph. Because this is flat, our acceleration is 0. Does this particular person need to be facing left and going that way? Yes, because here the velocity is negative. They are traveling in the negative direction. Do we know if they are in front of, to the right of the origin or to the left of the origin? They're actually to the left. We should actually probably draw our origin here. This particular one started at 0 and moved away, so they're right at the origin. This person here, let me see if yes, I did. No, don't copy the whole thing. No. Oh, I lost his leg. This person is running this way, and they've also started right at the origin, right? If they were to the right of the origin, like if the person was actually over here, if the person were over here, what would the graph look like? It'd be like this, wouldn't it? It'd be down. Like that, right? Running towards the origin, but it's not. He's over here. Okay. The next set of dt values is a speeding up. How can I tell Alex that this is speeding up here? It's not a straight line, exactly. It's curved. The slope is changing. The slope is increasing. Slope meaning our velocity time graph. So now our velocity time graph, it has a slope to it, right? The slope here is 0, and the slope gets bigger and bigger and bigger. This is a graph that is getting bigger and bigger and bigger. Let's say it goes up to -5. Here, my velocity is doing what? It's actually increasing.
Why is that -5?
Oh, not -5. I just picked a value. I'm just saying that it's going up to 5. Here, the velocity is greater than 0. It's positive, right? The velocity is greater than 0. It's like 1, 2, 3, 4. It's going up and up and up. Here, my acceleration is also, the graph in the book shows greater than 0. How can I get the actual value here? I would have to do my rise over run. So if that was 5 and that was 5, similar to the graphs we looked at yesterday, it would be this 5 over that 5, and the acceleration would actually be 1, wouldn't it, right? Meter per second squared. And then this time the person is starting at the origin and actually accelerating. Yeah, I always have to take the picture too. I can do it. I just need the picture in front of me. Back leg is straight. See, I didn't take any art classes, as you can tell. I'm just copying from the. You know the guys, the sports guys in the gym that are up on the wall. When I was in high school, I painted those. That's how I know how to do this.
Painted that
No, I made that up completely.
shit.
Pardon me?
I also painted that.
Yeah. Oh yeah.
Wait, no.
No, I just made it confusing.
Yeah, whatever, I helped cut out
So,
Store's gonna look good, eh? I think.
when is this supposed to be done?
Real soon, I hope.
Yeah,
That's nice. Okay, so there's the guy accelerating, and the origin is right there, right? Starting at 0. The next one here, we're going negative. Here the slope is also increasing, but it's becoming more and more negative, right? More and more negative. So the value of the velocity is becoming more and more negative, like so. Once again, let's just make an assumption that this is down to -5 and time is 5. So here my velocity is less than 0. It's like -1, -2, -3, -4. And my acceleration, if I use those values, the -5 and 5 would be -1. And the individual would be accelerating backwards. Okay.
I thought there's no such thing as negative acceleration.
No, there is.
There's no such thing as negative velocity.
Oh, right, it's not deceleration.
It's not deceleration yet.
You just lost that guy's arm. What
So
the heck?
negative acceleration is just moving in a different direction,
Ah.
and deceleration is.
How you doing?
It's just no. Deceleration is sort of non-scientific slowing down. There we go. All right, and origin being right there. Okay. How do we show slowing down on a DT graph? DT graph, the slowing down means that the slope is doing what?
Straightening out, flattening.
Flattening out. The slope is flattening out. So here the slope is flattening out. It's steep, then it's flatter and flatter and flatter. So the value of the velocity goes towards 0. Put the phone away, Mackenzie. Pay attention. Your mom can wait till noon to talk to you.
Oh, that's only one.
Here the velocity is greater than 0. Right? The velocity is greater than 0, but the acceleration is, here would actually be -1, wouldn't it? It'd be negative, right? The slope here is negative. So while the velocity is positive, the acceleration is negative, which means this particular person is pulling the Usain Bolt and slowing down at the finish line.
I don't know how to draw this either. Oh, you actually are just copying it.
Yeah?
I thought you were like trying to get. I don't even know.
I've drawn these a lot. It's not that hard, really. I've had a little practice. Now, oddly enough, this person is slowing down at the origin, at the starting line. They've already been running prior to the starting line. It's like the origin, the reference here is actually the finish line kind of, right? Because I can tell that because that's where they start. They start right at 0 and they're going positive, right? This particular graph shows slowing down as well. I can see that because the slope is becoming more and more 0. Here the value of the graph goes towards 0. The velocity is negative, less than 0. It's that negative because it's down below. but the slope here is positive, right? It would be up 5 and over 5. The acceleration here would be plus 1.
Wait, if, I have a question.
Okay.
If the T to T graph on the last one,
Yeah.
the velocity, what would you do?
If this graph were a velocity time graph, you'd be running negatively, and let me think here. You're asking if I had a VT graph that looked like that.
Yeah.
Okay, well this shows that the acceleration is going from very negative to almost 0.
You'd be like-
So you would be,
Oh, you can
you can't even tell which direction you're going from that. Oh no, you can. You're going left, right? Because it's below. So you're going left.
You'd be going like fast left and like slowing down.
Yes, you're actually speeding up going left and approaching a constant velocity. You're speeding up. You're not speeding up as much each second, and then eventually reaching a
Your
constant.
acceleration is changing.
Your acceleration is changing. Yes.
0.
Yes.
Would your acceleration be increasing or decreasing?
It's negative, but you're actually speeding up because you are going to the left. So you're actually speeding up. So you're actually speeding up at the start. You're consistently speeding up, but not speeding up as fast every instant. Yeah, so that makes your brain hurt. Okay, so that now this guy is just going the other way, right? I'll just redraw it. Sometimes it's easier to draw than flip. Okay, so some good thinking going on there. Definitely sort of keep track of that sheet. That's a good, valuable one to have. Okay, if you flip the page over, you'll see a beautiful flow chart, which I don't have.
Why not?
I don't know why.
Flow, grow.
You had the flow chart on page 48, probably because I didn't want you to sort of rewrite all of it. Okay, so how do you construct a VT graph from a DT graph? This is, relatively speaking, easy.
But they make it look really complicated.
They do. They make it look complicated. They're trying to make it simple. I don't know how well they did. If you were asked to construct the VT graph under the DT graph, break the DT graph into distinct motion sections and extend the times down to the VT graph. So what they're saying is when the graph looks like this, right, break it into, there's one section, there's another one, there's another one, there's another one, and extend those times down so that they line up. That's what they're saying. Okay, does that make sense? Then, calculate the slope at the start and end of each DT graph section. So what is the slope here? What is the slope here? Well, here the slope is approaching 0. Here the slope is very positive or negative? The slope right here is very positive. Okay, so my value is positive, and it goes towards 0. Why does it go towards 0? Because the slope there is 0. I'm going to say it one more time. What's the slope right here? It's positive. Does the fact that it's at 0 matter? No difference. It doesn't make any difference at all. It's the slope that matters. Going from DT graph to velocity time graph, it's the slope. So the slope here is positive. My graph must start in the positive region. I'm really graphing the slope. I'm graphing the slope as we go from left to right. Here the slope is positive. Here it's also positive, but less positive, so I'm down like here in a less positive area. And here the slope is 0, so my graph, my slope value goes all the way to 0. Does that make sense? Riley? Your mom can do without you too for a while. Hey! Alrighty, so now the next section here, what is the slope equal to on the position time graph?
0.
The slope is 0. Does it matter that it's up here at like say plus 15 or something other? We don't care. It's the slope that matters. We're graphing the slope. The slope here is 0. Here's the slope. It's 0, right? The value is 0. Does that make sense? Mike? I'm making sense? Okay, good. The next section, the slope goes from instantly 0, it goes to very negative. Sorry, it goes to negative, and then it becomes more and more negative, doesn't it? Right? It goes to more and more negative. So my value here, my slope, goes from 0 to very negative. Goes from 0 to very negative. Okay? And then at some point, the slope here appears to remain the same. It never changes anymore, and so the value actually goes like this. There would likely be a curve here, but I'm not going to worry too much about that. So really, all this is a graph of the slope of this graph here. That's all it is. And that's a pretty important calculus concept, too, for those of you that are taking calculus. Okay? I don't need to go through all that stuff there on page 49. They've made it way more complicated than I just made it. I think the way I just did it was outstanding. I should deserve a badge, I think.
Okay, well, give
Put
yourself
it up.
a badge.
Yeah? Okay.
While you're there, you know, might as well give me one.
How about we do the next one? The next one now is going the other way. This happens to be mind-boggling. Okay?
Perfect.
You really got to be focused here. Okay, I'm going to have to take a deep breath here and see if I can do this. Now we're going the opposite way. We're going from the VT graph to the DT graph. So you have to reverse your thinking. This is a graph of the slope of this. This is a graph of the slope of this. Okay, so slope here is very negative, right? I'm going to say double negative. It's very negative, here it's negative, and here it's 0, right? So the slope is going from very negative to 0. Note that this time lines up with this time here. It's kind of hard to do. I find like it sort of forces you to drawing them in the right shape. I'm not particularly recommending that you try and do this. I find it makes it a little bit hard. You don't have to put it right underneath. If it helps you, be my guest. Okay, so the slope is very negative and it goes to 0. Brett, I find that the 0 slopes start right there, right? So here, my slope has to be negative, right? Here the slope is very, very negative and it becomes less and less. So it's like this, right? Here it's very negative, not so negative, 0. Very negative, not so negative, 0. That's this first part right there. What's happening in the next part? The slope, remember again, this is a graph of the slope. The slope starts at 0 and becomes more and more positive. Becomes more and more positive. More and more positive, steeper and steeper. Now, you might say, why doesn't it, Mr. Bennett, why doesn't it go all the way to the origin? Let's go ahead and say that.
Why don't you go all the way to the origin?
Excellent question. Why doesn't it go all the way to the origin?
Because velocity,
Can you tell from these two segments here, can you tell somehow, or is this just a typo, or is this just fluke? How can you tell from these two segments, how do I know for sure that it doesn't go to the origin there?
See where things at?
Like, how come it doesn't go, what I'm saying is, how come the graph doesn't go all the way to there? Yes, you're right, Sean. It has to do with the area. The area down here is negative. The area up here is positive. If it were to start at 0, go into the negative, and then come back, if it were to go back to 0, these two areas would have to be the same. And in fact, if you look carefully, they're not. There's no numbers on there, but they would have to be the same for it to go to 0 there. What a wonderful test question. My goodness. It is. That's a real. It's so good. I think I forgot to put it on the test. But that's a great. If you know the answer to that, you get a lot of stuff. Like,
when is our test?
oh, not for a while.
Oh, okay, good. I mean, I've missed like 68.
Okay. Velocity time graph. What's happening here? What does this segment mean here? Remember, this is velocity time graph. It's what? Constant speed. How do we show that on a DT?
Constant distance away from the...
Constant slope. Right? Constant slope. Now, they've made a mistake here. What mistake have they made? This is a graph of the slope, right? It's going from 0, positive, to really positive. They've changed the slope here, haven't they?
Yeah.
In fact, and it's getting bigger and bigger and bigger, and then it remains the same. What really should be happening is this line should be at the same, it should be like this, shouldn't it?
Yeah.
That's what should happen.
So what should it, if you change the velocity one, that like, the box would just drop down a little bit?
No, oh, to make it match this?
Yeah.
Yes, to make, good question, good point. It would be like this, right? Yeah. Probably what happened was the graphic artist doesn't know the math and someone missed it, right? They should hire me to find stuff like that. Or Sean. Okay, next segment here. The slope goes from very positive back down to 0. And so this is good, right? This part is good. It's going from positive to 0. Positive to 0. Here the slope remains at a value of 0, so my slope is flat. And here my slope goes from 0 to negative, and so I have to make it negative. I have to twist it down, make the slope negative. I don't fully expect you to get all of that after one example. If you do, awesome. You probably need some practice. I'm going to give you that chance.
Yeah.
There's some questions on page 71. Some questions on page 71. I think they're in the back there at the green segment. Am I right? Yes. Okay. So there's some on page 71. You should do, it says 22 to 28. You know what? That seems like an awful lot. You do how many you think you need to get it. Oh yeah, we'll get to that. Yeah. Okay? I would say you should do at minimum 4. All right? Do it a minimum of 4. What do you have?
That's what I'm gonna get, and I'll say it one.
Oh, you do have a hand thing, don't you?
Yeah.
Okay. Hang on to that. Okay, so I'm going to give you this here. These are the graphs. They actually have spots for you to draw the graphs underneath. This goes with the questions. Do these. The hand-in happens after you've completed these, after you are feeling comfortable. I know what I'm doing. Do the hand-in.